December 25th, 2011. Millions of people just unwrapped new phones, tablets, laptops, and every single one of them opened Netflix. Netflix servers didn't crash, their CDN didn't fail, but across the United States, buffering everywhere. Christmas night, millions of people starting at spinning wheels. Here's the crazy part. The problem wasn't Netflix's fault. It wasn't their servers, their videos, or their internet connection. It was a single number buried deep inside a protocol written in 1981. My name is Bhavya Suresh, and today we're going to understand TCP congestion control. Not through textbook definitions, but through the real stories of engineers who had to break it, fix it, and reshape the entire internet because of it. Before we get to Netflix, you need to understand the problem they were fighting. The internet was not designed for order, it was designed for survival. Back in the Cold War era, ARPANET, the grandfather of the internet, was built with one principle. If part of the network gets destroyed, data should find another way through. No central controller, no traffic cop, just packets finding their own path. That worked beautifully for small data, emails, text messages, early web pages. But then came something the original designers never imagined: video. Suddenly, instead of sending a few thousand bytes, you needed to send millions, continuously, smoothly, without interruption. And the moment everyone tried to do that at the same time, something broke. Picture a highway, normal traffic, cars flow. But now imagine everyone in the city trying to drive to the same concert at the same time. The on ramps get jammed. Cars stop moving. On the internet, those jammed on ramps are called routers. And when a router gets overwhelmed, it doesn't send you a warning. It doesn't flash a yellow light. It just drops your packet, silently gone. And TCP's only way of knowing the network is congested is that silence. So TCP had to evolve a system to manage itself, a system that, as we'll see, would eventually determine whether your Netflix stream lived or died. TCP's solution was the congestion window, called CWND. Think of it as a throttle, a permission slip that says you're only allowed to have this many packets flying through the network at one time. Big window means fast data. Small window means slow data but safe. And TCP is constantly recalibrating this throttle. Every millisecond, it's asking one question: can I push harder or do I need to back off? The answer comes from four mechanisms. These four are the entire engine of TCP, congestion protocol. Understand these, and you will understand how literally every website, every stream, every message gets to you. Number one, slow start. Number two, congestion avoidance. Number three, fast retransmit. Number four, fast recovery. Let's build each one, and I will show you exactly where each mechanism shows up in real history. Slow start. When a new TCP connection opens, it has no idea how fast the network is. It could be gigabit fiber. It could be a congested 3G network in the middle of nowhere. So TCP starts humble. Congestion window at just one segment. But every time an acknowledgement comes back, every time the receiver says got it, CWND doubles. 1 becomes 2, 2 becomes 4, 4 becomes 8, 8 becomes 16. Exponential growth. TCP is sprinting to find the network's ceiling. Remember this moment because this exact behavior is what broke Netflix in 2011. We'll come back to it. Congestion avoidance. Eventually, CWND hits a threshold called the SS thresh, and TCP shifts from sprinting to tiptoeing. Instead of doubling, CWND grows by just one segment per round trip. Linear CAFL. 8, be- 8 becomes 9, 9 becomes 10, 10 becomes 11. TCP is probing the edge of what the network can handle, like a climber slowly feeling for the next handhold. And it keeps climbing until something falls. Fast retransmit. When a packet is lost, the receiver doesn't go silent. It keeps sending the same acknowledgement over and over, essentially saying, I'm still waiting for packet 47. Still waiting, still waiting. Three of those duplicate ACKs, and TCP doesn't wait for a timeout. It immediately retransmits the missing packet. This was a huge deal when it was introduced. Before fast retransmit, TCP would sit frozen, waiting for a timer to expire, sometimes for seconds. For video streaming, that's catastrophic. Fast recovery. All TCP after a packet loss would panic, reset CWND all the way back to 1. Start from scratch. Imagine you're driving on a highway. You hit a small pothole and you immediately pull over the restart of your car. That's what old TCP did. Fast recovery said, no, just half your speed and keep going. If CWND was 16, cut it to 8 and resume congestion avoidance from that. Put all four together and you get the sawtooth pattern. The most important graph in networking. Climb fast, tiptoe higher, hit a loss, drop, climb again. This was TCP's heartbeat, running right now on every device in this room. Back to Netflix, 2011 and 2010. Netflix had made a bet, the company decision. Move from DVDs to streaming. The future of the business depended on one thing: video had to start fast and play smooth. Their engineers were staring at a brutal problem. When a user clicked play, TCP would start a fresh connection. Slow start kicks in. The congestion window begins at one or two segments and starts climbing. For a web page, that's fine. A web page is maybe 50 kilobytes. And by the time slow start gets going, the page is already loaded. But HD videos requires pushing megabytes continuously from the very first second. And by the time TCP's window had grown large enough to sustain HD byte rate, the user had already seen the spinner, already lost patience, already switched to something else. The fix, when one engineer proposed, it sounded almost too simple. What if we just start with a bigger window? Instead of congestion window of 2, we start of a connection. What if we set the initial congestion window to 10? That's it. Change one number. They tested it. Load times dropped 10 to 15%. Buffering events fell sharply. Startup latency, the delay between clicking play and video actually playing, improved dramatically. But here's where the story gets bigger. Netflix didn't just patch their own servers quietly, they published the research. They partnered with Google, whose engineers had been independently reaching the same conclusion. They pushed it through the IETF, the body that governs Internet standards. In 2013, it was published as RFC 6928. The initial congestion window of 10 is now the default for every modern operating system. Linux, Windows, Mac OS, they all start TCP connections with 10. Because of work that began with Netflix engineers trying to stop a spinner from ruining Christmas. One number changed from 2 to 10, and it changed how every video on the internet has been delivered ever since. The Netflix story doesn't end with RFC 6928 because as video got even bigger, 4K live sports, billions of simultaneous streams, engineers started finding deeper cracks in TCP. Here's the fundamental problem with the classic sawtooth approach. TCP detects congestion by waiting for packets to drop. It inflates the window, waits until the router overflows, gets the signal through the dropped packet, then backs off. This means TCP requires packet loss to find its limit. It constantly pushes until something breaks, then retreats. That strategy worked in a world of wired connections. But in a world of Wi Fi, 4G, and 5G, packets get lost for reasons that have nothing to do with congestion. A wall between you and the router, a truck driving past a cell tower, interference from your microwave. TCP sees that lost things the network is congested, cuts the window in half, and your video stutters, even though the network was completely fine. In 2016, Google published research on the new algorithm called BBR, bottleneck bandwidth, and RTT. Instead of using packet loss as its signal, BBR directly estimates two things: the maximum bandwidth of the connection and the minimum round trip time. It builds a model of the actual physical pipe and tries to fill it precisely without ever causing overflow. Early deployments on Google's infrastructure showed BBR delivering throughput 2 to 20 times, 25 times higher than traditional TCP on long distance connections. YouTube's rebuffering rate dropped by 50% in some regions. Then came the even bigger leap, QUIC, which Google developed and which is now the foundation of HTTP 3. TCP had a fundamental architectural problem. It was designed at the operating system level. To change TCP, you need to update every OS on every device on the internet. That takes years. QUIC said, what if we build the transport protocol inside the application running over UDP? Now you can iterate, experiment, and deploy improvements in months instead of years. QUIC also solved a problem called head-off-line blocking, where one lost packet in TCP stream freezes everything behind it, even unrelated data. QUIC handles each stream independently. So a lost packet in your video stream doesn't block your chat message. Today, roughly 25% of the internet traffic runs over QUIC. Every time you open YouTube, Google Research, or Gmail, you're almost certainly using it. The engineers who fixed TCP's slow start didn't know they were setting the stage for TCP's eventual replacement. That's how technology moves. Each solution reveals the next deeper problem. So let's zoom out. We start with a simple question. Why does your video buffer at night? And the answer turns out to be a beautiful, messy, evolving story. The internet was built without a traffic controller, so TCP invented one. The congestion window, adjusting itself in real time, using slow start, congestion avoidance, fast retransmit, and fast recovery. The system worked, but it had limits. Netflix engineers found one of those limits on Christmas night 2011 and fixed it with a change so simple it was almost embarrassing, starting with a window of 10 instead of 2. And that fix revealed the next limit. That loss based congestion control breaks down in wireless networks. So Google built BBR and then QUIC, and the protocol that carries your video today looks almost nothing like what Juan Jacobson designed in 1988. This is what makes networking worth understanding. It's not abstract theory. Every concept we covered today, every mechanism, every algorithm was built by engineers who are staring at a real problem, often under enormous pressure, and had to find a solution that worked at internet scale. The lowering spinner, you see, that's TCP fighting for you. And now you know exactly how. See you in the next one.